Hey guys, welcome back to my channel. So this is class 3 on how to repair automotive ECMs. Today class is going to be about BJT transistors, and it's been a nightmare because I have been recording this class. This is the third time. I've been having so many issues with the recording. I'm trying to make it better for you guys experience and it's been a nightmare for me, but hopefully this time will work. So knock on wood. Alright, so I'm going to start the screen recording. That will be now. Everything is just the way it should be, so we're going to keep that here. Alright, so I have put some information together about the BJT transistors. Let me get my iPad here, and I'm going to put the information on the screen for you guys, which hopefully everything will be fine. I have the PDF already ready here. So again, I went a little bit online and got some images for you and some of the descriptions I could put together with what I know and what I could find in the internet. You guys can double check the information. So for you guys to understand, there is 3 types of BJT transistors. We got the NPN, the PNP, and the Darlington, which the Darlington is just a double NPN encapsulated together. So as you can see on the screen, we have the NPN is a bipolar transistors. So we have a compositive. So we have 2 layers of negative material with 1 positive layer of material. That will be NPN. And then on the PNP we'll have 2 layers of positive material with 1 layer in the middle, like kind of like sandwiched together to create what the transistor is, right? So these are also the symbols for each of the transistors. We will know that the PNP has the arrow for the diode facing in, and the NPN has the arrow facing out. This is very distinctive, and we will see on the class why is that and what it makes a difference when you are testing it with the oscilloscope, which I will have a virtual oscilloscope to do the testings that we are going to do today. I have a software that I want to share with you. It's called Circuit Wizard. Really good software. Hopefully you guys can get it. I think it's a trial version of the software that you can get. I will post a link. You guys try it out. I bought the software for myself for the class, and it's really good. Alright, so but coming back on what we have here, so again, I'm just going to read a little bit of what we have here. So it's a bipolar transistor. It consists, like I said, in a 3-layer sandwich together. We have the PNP and the NPN. The symbols that we have here, so for the NPN we will have the base, the collector, and the emitter. That's the way the transistors are. You have a 3-leg on the transistor. Let me see what else we have. Those are the symbols for each of them. The functional difference between the PNP and the NPN is the biasing polarity of the junctions when operating. So this is what I wanted to share this with you. It's very important. So the bipolar transistor work as a current control regulators. In other words, the transistor restrict the amount of current that passes according to a smaller controlling current. So the main current which will go from the emitter to the collector on the PNP, or from the collector to the emitter on the NPN. Hopefully I'm saying it right. Looking at the images and you can compare it. So if we have the arrow in, like I said, so we have the arrow in, that is the PNP. We have the arrow out, that's the NPN. So PNP, NPN. So this is the way the current will go on the one on the left, PNP, right? So it's going to keep going like that, right? So we got the PNP on the left. The current will go from the emitter to the collector. and is being controlled by a small current from the base, or in this case from the emitter to the base. The others, the NPN, is the opposite, is from collector to emitter, and is controlled by a current that goes from the base to the collector. So that's pretty much the difference in between these two. As far as we can see here, activation wise, we need to understand, and that's the way I always have seen it myself. On the NPN, the P is in the middle, so the NPN will be activated by a positive signal. Let's disregard the voltage. It can be 5 volts, it can be 7 volts, it can be whatever, right? It has to be the high side of a signal. The PNP will have a negative activation, which is not really a negative, it's a low side activation. So in this case, 0. It will be very important to see that on the oscilloscope, and we will find out why. So the Darlington, it's just the difference in between the Darlington and the NPN is pretty much the same. It's just two of them together. It draws less current and it can manage a higher load on the collector emitter, because it's a double transistor, and it works very, very good because it draws less amperage on the base and it can handle higher loads. All right, so I also put together some sort of examples for you guys to get familiar with what this transistor look. So this is an image of a BJT. So we have the 3 legs, base, collector, and emitter, and this specific type of a transistor has the collector on the back is accessible too. So sometimes you cannot use this leg or something, you can use the collector on the back as well. So as I mentioned before, and it's a repetition in here, but this is the way you will probably see it on, on the automotive application, right? So we will have, this is the PNP, so we will have an activates with a, with a low signal, again the N, low signal. So if we have a square waveform of 0 to 5, when it reaches a 0, it will turn it on, and when it goes up to 5, it turns it off. We got the same explanation about, the current that turns it on from emitter to base, and then how the large current flows from the emitter to the collector. So in this case, the PNP, the emitter is connected to power, and then the load, in this case, I draw like this, let's think it's a bulb or not a resistor, but in the collector we will have the load. We can have, a motor or something, obviously a small, that will be controlled by this. And I'm just giving you general information, right? We will see on the board more of the application. So now if we see what the NPN does, is again the automotive application. I just put the same image. We got base, collector, and emitter. Again, the back is also the collector. With this one, it activates with a positive signal. So again, 0 to 5 is square wave. When it reaches 5 or 12, which I also put in here, is usually on the automotive application, and I forgot to mention that in here, we will have a resistor to protect whatever is on this side. So again, it will activate with a positive signal, and then the way the current goes, so it goes from the base to the collector. That's the activating current, and then we will have a load on the collector, right? And what the transistor will be supplying for this load is the ground, which is connected on the emitter. Now we have the Darlington. I just did, small drawing. I put this with my iPad in here. But you can see that, the NPN does the same, NP, so it's activated with a positive charge, or not a charge, a positive signal with current. Very important, and I have to address that because you can have, 5 volts and no current, it will not work. So it's not like a huge amount of current on the side, but for the circuit board it will be huge, so it has to have current. Again, it goes through a resistor on the base. The collector will not activate, will have the loads looking or waiting for the ground, which will be supplied by the emitter. That's my stomach, sorry guys. I'm a little hungry, probably. Long day trying to make this work. I swear sorry, I shouldn't swear. I tried this 3 times. I've been trying to use this recording software, which is really good, and I don't know why I was messing it. I tried to do the editing with Adobe Premiere, which I have used for years, and it's a footage error. I tried for like hours. I should have just recorded, and I tried to record it again, and it failed. So again, that was my mistake. So if we connect an oscilloscope on the base of an NPN transistor and the emitter, we will see the voltage drop across the diode. I should put in there voltage drop. So if you guys are there, please just put it in there, drop, because that's what we're seeing in there. It's just a voltage drop across the diode, not the resistor, across the diode. And then the signal will be a 0 to 0.7 volts from base to emitter on an NPN transistor. Why? Because again, remember, the NPN is being activated with a positive. So if we have, let me go back to the NPN. That's right here. So we will see this on the application. So when the NPN, which is supplying already, we have a ground in here, so it's connecting. When it disconnected, this goes to 0. So if we check it in here, if we would have checked this transistor in here before the resistor, then we will see the whole amplitude of the waveform. I'm talking about in the base. Very important, because the two it's a very big difference on the signal depending on where you checked. But if you check the transistor, that's the way we do on electronics, right? You go right to the components. If you check from base to emitter, you will have a 0 to 7, I keep saying that, 0 to 0.7 volts waveform. And that is completely normal. So you will see the activation as just a small signal. All right, going down into the writings that I have for you guys in here to read too. If we connect the same thing from the base to the emitter on a Pnp, we will see again the voltage drop of the diode, but it will be from 12 to 11.3. It's still the same 0.7 volts, drop, but it's just starting at 12 volts. Why? It's again, we are on the base of the transistor, so right here. So we are supplying power, and again, this application is not 100%, but all the time on these transistors, there will be a resistor in here to the base for protection. So whenever the transistor is off, you will have 12 volts in there. And when it drops, which is on and off, it will just drop to 0.7 of a volt. So you will see it in a second. So let's keep going with the explanation. The difference on the Darlington is a double NPN transistor put together, so externally it's pretty much the same. But since it has 2 diodes, if we measure from base to emitter, now we will have a 1.4 voltage drop across those 2. If we go again before the resistors, we will see the whole amplitude of the waveform. So I also have this software that I was talking to you guys. I have something else in here that we will be putting together a pulse generator for you guys to do some checks. But let's keep going with this, and I'll show you in a second what we're talking about. That's just a little bit of a giving you what is coming next. All right, so let's bring this down. So again, the software name is Circuit Wizard. I will be putting a link in the description for this software. Since this is the third time, I know this information, you know, like I own it. So I already have this design. I wanted to do this with you guys, but you know, since again, it's been happening, many problems with this, it's already done in here. So it's a very nice and intuitive software for not just drawing, it's also a simulator. And it has amp meters, voltmeters, oscilloscope. It has analog, you know, as a test equipment. It has a lot of stuff. Let me show you right here. So if we go, again, you can go into gallery and then scroll down into test equipment or test instruments. You have, like I said, yeah, ammeter, voltmeter, test points, and all these different test equipment. It has even a word generator. If you want, you can put a speaker in here and it will start talking to you. So it's very, very nice. So please, if you can get it, I want to guys to have this software so we can interact. You guys see what I'm doing, and then you can put it together, because this is not just a toy. No, this is it's good for me to teach you what I'm, you know, explaining here, but it's also good for you guys to first draw the system, you know, do the schematic of what you need. You can check it, test it, it works. Then now you can build it, because in here you can specifically put, you know, what type of resistor you need, what type of bulbs, or etc. So let me show you just a little bit. So what you will do is, again, drag from here, just drop the menu. You can go to power supply, just click into anything. You ain't going to destroy anything. I mean, this is just sub menus, and look what is in there. Switches, we have all these switches in here. Resistors, we have all this type of resistors. You can have, you know, pack of resistors together that share the same ground, all the same power, depends on the application, right? So you can have potentiometers, variable resistors, and etc., right? So it's very nice. So all you need to do, let's say, you know, I'm going to, sorry, let me go out to power supplies. If I can click in there, power supply. So all you need to do is just get in the symbol and drag it into the board. This will be like a protoboard, and it's exactly the same thing, because what you will do is I'm putting a resistor in here, and then you have the power rail, the ground, and again, I am using it this way or doing it this way because I don't have all the stuff that I need for this applications. I'm looking for 2 of the volts that I'm missing in 1 resistor. I have a box of all the things that I bought, and I didn't want it to like waste the time on that, because I have this software too. If you don't want it, whatever you put in here, you can just delete. Just click on it, right click, and then delete. You can also delete any sectors of harness that you have put together. Like in here, we have, you know, this is a bulb. If I click, right click, and then go to properties, we can see there is a 12 volts bulb that draws 100 milliamps. So that is very good. And I should show you that too. In here, you can drop the menu. You can select all these different bulbs, up to 240 volts with 20 milliamps draw. So it's impressive. All right, if we go there, we have, you know, if we stand on the tab, it tells me that this is an NPN transistor, that this is the base of the transistor, which is pin 2. Very important to know which pin is the base. Also it tells me the collector is the upper one, and the pin is the pin 1. And then the emitter is the pin 3, and it goes, in this case, the NPN is the ground, right? So in the motor or automotive application, this is the way we will see the NPN connected into the board. So we will have on series transistor that goes from it just proceeds over to, in this case, the switcher will be on the controller side on a computer, and then a parallel resistor to ground. This one in here is to make sure that when this one is off, anything that is left over here that disconnects, it is also, for the current and everything. So to make sure that the transistor turns off. And also as a protector. If you want to change the properties of this transistor, again, is click on it, right click, and then you can change, you can check, you know, up to 5 watts transistor, oh sorry, resistors, and you can check, or keep saying check, you can change anything you want in here. You can change the name, you can put a caption, you can change the value, and it will also tell you, if you stand on it, what the color of that a specific resistor with a you know, a quarter watt is red, black, red, gold. So I hope you guys remember. If I go over to my browser and I open here the resistor color calculator, and we pick on for those that don't know how to that, you know, what is that, I will put the link again. This is all about circuits, and we have that calculator in here. This is a very good site, DigiKey. If you need some components, they have a very good assortment. I use it a lot. So we have in here red, black, red, gold. So red, black, again, just one more time, red, black, red, gold. And we go here, where is it? Right here. So we put red, okay, red, black, red, and gold. Actually, I have it already. Why is it showing different colors? Red. It's not showing the colors in here. Usually it shows it. Red, black. It's showing different colors in here. But well, if you see it right here, and it's showing me, you know, it's a 2K, the tolerance and everything. So it is good. I don't know why it's not changing the colors in here. 2 black, red. So, but that's the way. So we know as a fact that that is correct. And I mean, the software is very, very accurate. So what we can do with here, so I put a switch in here to simulate what the, you know, controller will do, which is, you know, on, off, right? But we have no current, which actually, you know, what the bulb will be. So if we put an ammeter, we can read the current, and we will do it in a second. So if I run this project now with F9 or going into project at the top, now this is live or on. See, the bulb is coming on. So that means that all my connections and everything that I'm doing, I've been able to activate this transistor, and it's working. So we can, again, that's why I wanted to be in, use this software. If we put, you know, an oscilloscope, I'm going to put an oscilloscope in here. I'm going to need another ground that I erased before. Bear with me, guys, because it's a little time consuming, but it's important. So if we put, you know, 1 lead, when you want to turn, just release the mouse and then click again when you want to go up. We're going to go to the bottom, to the base of the transistor. If you are, you know, on the computer, you will be, you know, using the emitter. I cannot jump the lines in here. This is just symbols, you know. The actual reading will start when I select in here and I go add a graph, or you can click up here, and you can also click, you know, add a probe. Where are we? Which one are we checking? I have already set up it here, another one. All right, so we can add a probe. Before I do this, guys, and I want to address this, make sure that you only have one probe. Oof. Get that off, Control Z, right? I want to delete that probe from here, so we only have one reading at a time, because otherwise when it runs, it will start reading anything that is in there. So we can make this graph a little bigger, and now we can click in here, and we can now select what says add a probe, and we're going to put the probe right where we're taking the measurement. This is the actual measurement. So now when we run this, and actually let me do one other thing, which is an amp meter. AC current source. Now let's just go to distance instruments, and we're going to put an amp meter. So let's just put it here for now. one thing that we want to make sure is when you're putting an ammeter, it has to be polarity sensitive. So we want to make sure, let me erase this 1 second, guys, because I need to have a little more room. I'm sorry it's taking a little long, but I mean, it's important for you guys also to get a little familiar with this software. So if I put the amp clamp, or ammeter, not an amp clamp, in here it has to be the positive, on the positive side, and then not that it's a negative, but you know, the other lead after. Now your reading is going to be correct. Alright, now if we run this project, again F9, we can run it, enable to simulate this circuit. Due to one or more, there might be a false in the circuit. Alright, so we have an error. Let me see what the error is. I don't really get it. Well, let's try it one more time. If you recommend to try lowering the simulated time based on your solder circuit parameters. Alright, this is weird. Let's delete the amp clamp because I think by having it 2 is creating a problem. Nope. Where is the issue? Channel 1 probe, that should be, there's nothing wrong with here, so maybe it's just a bug. So let me turn this off 1 second, guys, sorry. And let me open it up again. Try so many different things that sometimes software don't like that. Alright, so file open, right? In my case, in your case, you're gonna have to do new. So BG, we have it here, and we can open it. I'm going to erase this for now here, like that is no errors. And if we run this, there's no errors. So we can stop and stop. Now let's put the oscilloscope as we need before. We're gonna just go out to the base of the transistor, that's good. And that's good. We're gonna add a graph. Oof, that's a little too much. Very nice for the graph, but now we cannot see the rest. Come on. Right here, so let's just do this a little smaller. Again, let's add a probe. We're gonna put the probe right at the bottom of the transistor. Make sure that there is not a probe, and it is. So we're going to delete that. I don't know why it's doing that. Graph. Oh, I know why it's doing that. Let's delete that. And we can delete that. So we can actually, let me see. Let's add a graph. Now we have the graph also here too. And I just learned that by doing mistakes. So if we run this, I got low, up. So we can see the graph up there, which is very cool. Let me stop that, just pause it and remove. it's not because it's, well, it doesn't matter. So what I wanted to explain, I know as I'm going to everything, this is again our NPN transistor, and we have an activation, as I explained you guys before, from 0 to 0.7. And why? Because we're seeing what is going on from the base to the emitter, which is the ground on this case, right? And we can do the same thing. In order to erase that, I gotta stop the whole thing. So we can do the same test, and I'm going to erase that from here. Yeah, that's the easiest way. Our next transistor is our PNP, right? So we have the PNP transistor. Then we have, you know, on the emitter, we have a 12 volt, and on the collector we got the load. The load is waiting for the 12 volts to go through the transistor when this gets active by a low signal, which is, that's what I'm trying to do here. With this, we have another 2 resistors. We got one in series, 1K, and then another one on parallel with, but very important, we had before resistor 2 going to ground. In this case, resistor 2 goes to positive, because this is being activated by ground, right? So if we run this and we try this one, we got light, so it works. Everything is good in here as well. I know, guys, it's a little time consuming, but believe me, you will understand what I'm doing this, why I am doing this when we see the pulse generator. It's very important to understand that how the transistor works on a computer. This is part of that, and also it's going to be very handy when we fabricate our pulse generators. So you're going to be able to create a 0 to 12, a 0 to 5, or whatever you need pulse, so you can control what is the low side and what is the high side. And we will be having a lot more control when we talk about the MOSFET. So just get the Protoboard. That will work, because we will be changing those BJT for MOSFET, but in the control will be more accurate. We can increase 0 to 100 as far as the frequency, and then we can change also the low and the high. So we'll see that in further classes. So if we do the same test in here that we have with the oscilloscope, I'm going to put the oscilloscope now here. This way. We can connect the ground in here, and I can go with this to the bottom of the transistor. Perfect. And we can add a probe, which hopefully I remove from the top. Yes, I did, right? No, it's still there. Try always to have one probe, please, because otherwise it gets confusing. Alright, so if we run this one more time, remember we have a 0 to 7 before. Let's see what happens when I activate this one. Now it's going from 12 to 11.3, 12 to 11.3, 12 to 11.3. Let me pause this. So we have, 1 volt per division on the left side, and then 2 seconds per division for a 60-second capture on this screen. Let's think that you're using your scope. Hopefully you guys are familiar, otherwise this will help you to get familiar with connections of oscilloscopes, of ammeters, voltmeters, and etc. This software is very, very, very good. If you guys want, I can also put a voltmeter here, which is, good too. We can go up to the same ground, and then to the same location, and now we will have a reading in here. So if we clear this data, clear the results, and we're going to run it again. So the amperage the voltage is 12 volts, 1115. It's actually reading in here, but you see the bulb is coming on. That's the activation. So now we not only see the waveform, we can see the actual voltage drop. So we know that we're going from 12 to, in this case, 1115 On the other one, we were going from 0 to 0.7. So there is a huge difference. This is still the same voltage drop of 0.7, but since one is activating by a low pulse and the other one is by a high pulse, we're getting this difference. So if we go now to the Darlington, which is our last test for here, we got the same situation as an NPN. Okay, the two resistors, one in series to the IC, or in this case a switch, and the other one to ground. And then the load in this case is on, well, we have to go here. We will have the load on the collector, and we will have a ground on the emitter side. So what will this bulb be waiting for is for a ground when these two transistors connect. So we can run this and make sure that, you know, our drawing is fine. So yeah, the light's coming on. So everything that we have here is working as it should. Now we can take measurements as well. Let's put our oscilloscope in here. We're gonna go the positive lead to the base of the transistor, and we're gonna put a ground lead to ground. Then we can put also, just to save time, a voltmeter, and we can connect the negative to this ground in here that I just put. Remember, this is just because I cannot throw many lines on top of the other ones. In our case, we will have probably just one ground situation, right? So we can avoid all these wires. I click every time I need to avoid, you know, do a turn. So now we have everything ready, and then again we can run it and we can see the measurements. Is this on? Yeah. Oh, I forgot to put our probe, right? So make sure our probe is still here. See, that's very important. Done. You can move the probe, but don't forget to either erase it or move it, because it wasn't starting in 12. I'm like, why is it starting in 12? That's, my voltmeter is reading right. So let's clear the results again, and we can run this and press the switch. So we go from 0 to 1.61 in this case. 0, 1.61. 0, 1.61. So this is, again, telling us we have a voltage drop through the diodes of the transistors. So two diodes, 0.7 volts each, 1.4. Again, the tolerance is a little different, and we can have a little less, a little more, and you will see that also on the boards. And that's why it's also important to do all these testings. I mean, you can get familiar without, you know, having a computer, and where do you need to do the tests. We know the picture of how the transistor looks. We will look into that on, you know, on the computers, and we will see that on next classes. So don't worry. I know that a lot of guys are like, can we check on outputs and inputs and all the stuff? Yes, we will. I want to make sure that we start with the basics. We need to have a good foundation for everybody, not just the old-timers or, you know, a lot of experienced techs. They are also part of my subscribers. We also have, you know, beginners and new techs that are not familiar with electronics. We need to make sure that those two understand, so we can all get together. No matter what, reaffirm your, you know, your knowledge is important. All right, so let's proceed. So these are the three. This is the Darlington. Again, it's a cascade of two NPN transistors. The next thing that I wanted to show you guys is, going back to my PDF, we're going to create a pulse generator. For this, we're going to use a timer. It's an IC chip. It's called the NE550 or 555. Very common, a lot of people knows what I'm talking about. To know which pin one is the one next to that, kind of like half a moon cut with the dot. So this will be pin 1, 2, 3, 4, 5, 6, 7, and 8, as we have it here. You have, if you want to read, which one is ground, which one is trigger, which one is the all the pins on the timer, the threshold, control, etc. What we're going to need as far as materials to create this timer, you're gonna need an NPN transistor, a PNP transistor, you're gonna need two 10K resistors, you're gonna need 100 microfarad capacitor. That is for the system. For the actually control side of the 3.5, we need to have a 10 nanofarad capacitor that will shut down when it's off. So anything that is left over will make it to ground. So I also said in here, if we add some transistor, we can actuate loads with the timer on the 555, because this is just a timer, right? So we need something else to actually be able to control a load. Like you know, you truly can control anything you want with this. Further down the road, I'll explain you how. I'm going to put it here just to turn two lights, one on, one off. It's going to have different times, and I'm going to show you the formula that is based on these resistors and capacitors that I have in here. So we have to calculate the time high and the time low. So I put TH as time high and TL as time low. So the formula for the time high is 0.693 by resistor 1 plus resistor 2 by the capacitors. Make sure that you understand that these two are inside a parenthesis, so this has to be done first. So add the two resistors first, then you can do the multiplication. For the time low, we have just 0.693 by inside parenthesis, so this again, these two first, resistor 1 by the capacitor. So the resistor, the time high is again the 0.693 by 20,000, 10,000, 10,000 plus 10,000 by 100 microfarad capacitor. This is how you put them in numbers. So it's 0.3 zeros and then 100. If we add and multiply that formula, the time high give us 1.38 seconds of time high. If we do the same on the time low, again, do the formula, the result is 0.69 seconds of time low. So by knowing this, now we can connect time high and NPN, right? Time high, so it's good. We need to activate a NPN transistor, and then when the time low, we can use a PNP transistor to get those lights on and off. So we can also, by adding the two times together, we can know the hertz. And this is the formula in here. You can see it. So it's actually this transistor hertz-wise is 0.480 hertz. So that's pretty much what we have. And this is what we will do with the whole thing. So this is again the drawing. We will have a 12 volts, resistor 1, resistor 2 connected to 7, 6 and 2 are together after the second resistor, and then two other capacitor of 100 microfarads. 8 and 4 are together on the power side. Those are the reset and the voltage. Pin 1 is the ground, and then 5 is the control, 3 is the output. This is actually not the way the 3.5 looks. We saw it in the beginning. The pins are counterclockwise and goes from 1 to 8. But this is just to make it easy for you to see how it's connected. So looking at the signals that this timer will produce, obviously it's going to produce a 1.3 something high and then a 0.6 low, right? So when it goes high, we will be activating an NPN transistor that will go through a resistor. We're going to need a 220 ohm resistor, and then another one. I didn't put the value of this one, but I have it on the actual circuit wizard. We'll see it in a second. And then we're going to have a ball going into power. So just to read this, we're going to have the other side, which is the low side. We need a 2K resistor and a 4.1K resistor that will go to power to activate the low side bulb. that's a quick description of what we need. So now I'm going to open the pulse generator file, and we're going to do some tests as well. Okay, so we got the same thing that we were looking at before in there. So let me just make this a little smaller so it fits good in here. Disregard the grounds, those are for the next tests that we're going to do in here. Also, all these rails of power, they just will go to the same power that we're using for the timer, because otherwise it will act weird if I don't connect this in here. If I try to turn that off, you'll see that the light will stay on. So right now, if I run this, you can see we have a light that stays on for 1.6, 1.39, whatever it was on there. So let me go back to that 1 second so I can read that. Okay, so yeah, the time high is 1.38, so let's say 1.4 seconds on, and the other one is only 0.7. So BL1 is the one that's staying high, and the BL2 is the one that's staying low. So the activations are different. But yeah, the system is working. So, but yeah, you'll see, well, what we need this for. Again, with this, you can control a cam sensor, a crank sensor. You can make that signal to control or to simulate those signals for the same computer. Because you saw me on the first 2 videos, and that's why I wanted to share that at least at first, so you understand what this is for. Because not everybody is going to be able to have, a computer simulator, and even sometimes this is not enough. I have some other equipment I will be showing in further videos is also for that, because I need to create different signals. I need to then read my oscilloscope, calculate what is going to be my low time, what is my high time, and what is my frequency. Then I can do an activation that I can with that piece of equipment, which I can connect that to the computer and then get some signals and change, like it has some like custom area, but it's very limited. So with this, we can calculate, we can do our own stuff. And the more we go, the deeper we will be able to do things. So just bear with me, guys. I know you're gonna like it. All right, so let's turn this off for 1 second. I want to, again, use an oscilloscope. If you guys want to have the real thing done, I'll probably do it, but I mean, I think this is very good. All right, so we're gonna put an oscilloscope. Let's see if this side works. I think I put it in last time. Actually, right here. Yeah, the oscilloscope will fit a lot better in here because I can go if this let me. Trying to go to the transistor base in here. Let me move this ground so a little bit out of the way for the other one, and then we can go to on channel 2 to the other transistor, right? So we can see first the 2 signals. Let's just start with those 2 signals. We already know that one is going to go from 12. I should have put the voltmeter. Try to save some time. Let me think on what I want to do, because it just gets so crowded that it's sometimes hard to understand what I'm trying to explain you guys. Believe me, I tried 3 times already. So if we run this now, oh, I forgot to put the probes, right? So we need to add the probe right in there, and then a probe right here. So now we can see the activations of both of those transistors with the 3.5. We don't need to do anything else, right? The 3.5 is controlling everything, so now we can see those waveforms. You'll see, but yeah, those waveforms are really small, man. I cannot really use that for much. Well, that's what you think. It will work, but remember, our signals are not there. So if I stop this now, let me clear this data. This is the bottom of the transistor. We also have the real signal, which is the on and off that this transistor is doing for the load. That will be our output going into our computer. The simulator is sending those right here on those connections, right? So let's run this one more time. Now we have two signals, right? And the nice thing is they're both the same, right? That's funny. I think I got a little off track just to show you this. But this is a little further on it. Let's do the activations, the high and the low, because otherwise you get confused to what is happening in here. I can just show you or tell you that even with this signal, then we can now put another transistor and get more activations for, creating other signals. Because if I go over to the same transistor on the input and the output, and that's why they're both, if I choose like that, they were all the same, they're not. Because remember, one is on and one is off. It's truly not the same. Let me clear this data. That's the way I should have shown you. So right now I'm in the same transistor. Disregard the connections. That's just a drawing. The actual test is happening where the probes are. So right now we are in the bottom of the transistor and we are in the load, or in this case, if we step in here, we're in the collector. If we run this, now we can see what is happening. Let me just go a little bit and we can pause this. So remember, and now we have blue signal on to 12 volts, right? That's just the volt side, so it will have 12 to 0. But when this one is on, we have a low signal on the activation of the transistor, right? So this is this gotta be what, the Pnp? No, sorry, the MPN. So this is the NPN, and then we have high, but the signal is low, low, or high, and the signal is low. So the signals are opposite. And then we can with that control different outputs too, with the same 3-5. Remember, this is going high when the other one is low. The time is going to be, as we already discussed, we will have a time high of 1.4 and a time low of 0.6 seconds. Very quick, very easy. We can also, put, let me delete up. In order to change or do any changes in here, you need to delete to stop the actual simulation. Then now we can delete that and put it anywhere else we want. I was going to show you, and I forgot to do that on the Darlington and on the NPN. I'm a little tired trying to do this through the day. The actual Darlington, it draws less amperage than a regular NPN. That's what is also nice about those transistors. Since the base draws less amperage, it's better for any IC chip or controller that you're using, and it can handle a bigger load because of the way of the design. So it can go up to 10 times more. I don't know if I tell this on this video. I get a little bit confused of 3 times trying, right? So please bear with me on this. What other check I would like to do in here? So we can see, we saw the voltages, we can see the activations. Let me see if I put, I like to have, you know, different graphs. It's a little sad that we cannot move channels in here. The signals will just go, like in your oscilloscope, you can bring one channel up and the other one down. I don't know if I can. It's just, again, bear with me. It's my first time. Well, not my first, my third time using it. But so what we can do is put a voltmeter in here, and I'm gonna have to put the oscilloscope back again in there too as well. So we can run these tests, one more test. Click stop. We got a ground in there, and we're gonna put, we know this here is 0 to 7. I want to show you guys the reading in here when this is being activated. Again, if we run this, oh, forgot to put the Pro, right? I don't mind doing this, you know, I like to get familiar with the software that I'm using. So now we see the activation. If I pause this, I want to make sure that I pause it when it's low. It's pretty much instant, right? So we are actually getting, and the difference on what I was saying about the signal being opposite is when this is low, the actual reading in here will be 12 volts. Why is 12 volts? Because it's going through the load, right? So that's very important. That's why our signal, if I put, you know, an oscilloscope in here, it goes different. Why? Because we got a 12 volt supply going through this, so the signals are opposite. Very important. Still, the time will be the same, but it is really very good to do different waveforms. You can have one signal coming from the activation of the transistor and another one from the actual load side. So that's, you can do that. Why? Because it's opposite. So this is, you know, a different activation on the, you know, on the pot, on the collector on the collector of the transistor. Difference in here, you know, if we do the same measurement, it will be the opposite way. The signals on these is going to be very close together. Remember, we have a 12 to 11, 3, and this will go from 0 to 12. So that's the difference. This one is going from 12 to 0. Even though you can think it's the same, they'll start in different. This starts from 12, and this one, the one on the right, it starts on 0. So again, guys, I hope you can put this together. Let me just remove, I have to stop the software again. I can close the graph side. I'm going to remove all the test equipment from here so you get a better view of the actual design that you need to, you know, to do in order to have that pulse generator that we will be using to create signals. So please do it. I want to have interaction from you guys, make the class a lot more exciting for you and for me. I know that you guys will start making questions. So I did this test and it didn't work, and that's what I want. You know, I want you to try it, make mistakes, ask me, learn. That's the only way you can learn, you know, try it out, because it's not the same when you have it on writing than when you actually try it. So let's put this together and make it happen, because we're going to use it for activating some. I have some old computers coming from a Nissan and Tracker. I have a few for Toyotas in here that we can use for those signals, and then we're going to tweak it later on to use it on the new stuff with the MOSFETs, because that's what most of the computers now use. You use the MOSFETs and the IGBTs for bigger loads. We can use all those too. So just bear with me, stay, and you're gonna be learning a lot. So I'm sorry again for all these changes. It's again in my brain a little hard to make sure that I'm giving you all the information in the right way, especially after the third attempt. It's been very exhausting for me, but I want to make sure that I give you the class for Monday. I'm trying. I had Saturday off and Sunday off, and I'll be using it all for this, and hopefully it works this time. So guys, hope you like class 3. I'll see you next time. Don't forget to subscribe. Please tell your friends, whoever you think is going to take advantage of this information, to subscribe to the channel. And I would like to read your comments. Please give me advices on what you want, what you like. Is the audio good? I mean, sorry today, I don't have my noise canceling, but at least it's quiet in here. And we'll see you next time. Thank you so much. Bye-bye.